Every time something rotates smoothly, a car wheel, an electric motor shaft, a jet engine turbine, a wind turbine, even the fan inside your laptop, there is one small component silently doing the most critical job: the bearing. It is one of the simplest-looking mechanical elements ever designed. 2 rings, a few rolling elements, maybe a cage. That's all. And yet, without bearings, modern civilization would quite literally grind to a halt. The core problem a bearing solves is fundamental physics: friction. If you like similar educational videos, please like, subscribe, and share the video with your friends. Whenever 2 surfaces slide directly against each other, resistance builds up. Heat is generated, energy is lost, surfaces wear down. Eventually, they seize. If a steel shaft were to rotate directly inside a metal housing without a bearing, the system would fail very quickly due to sliding friction. So how do engineers solve this? By replacing sliding friction with rolling friction. Instead of allowing surfaces to scrape across each other, bearings insert rolling elements, balls or rollers, between them. Rolling dramatically reduces friction because the contact mechanics change completely. The energy required to keep motion going drops significantly, efficiency increases, and component life multiplies. But a bearing does far more than just reduce friction. A bearing must support loads, maintain precise shaft alignment, allow controlled rotational motion, withstand repeated stress cycles, operate under temperature variation, survive contamination and vibration, and it must do all of that at the same time. Here's something many people misunderstand. A bearing does not eliminate contact stress. In fact, it concentrates enormous forces into extremely small contact areas. The engineering challenge is not removing stress. It is controlling and distributing it safely over millions of cycles. This is why bearings are precision components manufactured to microscopic tolerances. Surface roughness, internal clearance, material hardness, lubrication regime, every variable matters. There is also no such thing as a universal bearing. A bearing designed for high rotational speed is different from one designed for heavy shock loads. A bearing built for precision positioning is not optimized for extreme radial force. So before we explore why different bearing types exist, we need to understand something deeper. What actually happens between the inner and outer ring when a bearing rotates? At first glance, a rolling bearing looks deceptively simple. 2 rings and a set of rolling elements placed between them. But inside this compact geometry lies an extremely precise mechanical system operating under high stress and microscopic tolerances. Every rolling bearing consists of an inner ring mounted on the shaft, an outer ring mounted in the housing rolling elements, balls or rollers, often a cage which separates and guides the rolling elements. The critical detail is this: the inner and outer rings never directly touch each other. All loads are transferred through the rolling elements. When the shaft rotates, the inner ring rotates with it. The rolling elements begin to roll along the raceways of both rings. But this is not perfect rolling in a pure mathematical sense. In real mechanical systems, there is always a combination of rolling motion and microscopic sliding. This is where bearing geometry becomes essential. In a ball bearing, the contact between the ball and the raceway is essentially a point contact. This minimizes friction and allows very high rotational speeds. However, because the contact area is small, the stress at that point is extremely high. Bearings operate under what is known as Hertzian contact stress, where load is concentrated into tiny elliptical contact patches. In roller bearings, the contact is line contact rather than point contact. The load is distributed over a longer area, allowing higher load capacity. This comes at a cost: increased friction and lower maximum rotational speed compared to ball bearings. The raceway curvature is carefully engineered. If the curvature is too tight, stress increases. If it is too loose, stability and precision suffer. The geometry ensures proper load distribution and prevents edge loading. The cage has a subtle but crucial role. It does not carry load. Instead, it maintains even spacing between rolling elements. Without a cage, rolling elements would cluster together due to centrifugal forces and load distribution. This would increase friction, generate heat, and lead to rapid failure. Manufacturing precision is another critical factor. Bearing surfaces are ground and polished to extremely low roughness values. Even microscopic surface imperfections can act as stress concentrators. Over millions of cycles, these micro defects can grow into fatigue cracks. And that leads to an important insight. Bearings rarely fail due to a single overload event. They fail due to fatigue over time. Each rotation applies stress. Over millions or billions of cycles, microscopic cracks form beneath the surface. Eventually, material spalls off, and the bearing begins to deteriorate. So a bearing is not just a friction reducer. It is a controlled stress management system operating at the edge of material limits. Once you understand how a bearing carries load through controlled rolling contact, it becomes clear why there is no universal solution. Every machine imposes different demands: speed, load direction, shock resistance, stiffness, alignment tolerance, lubrication conditions. Each bearing type exists to solve a different engineering problem. Let's start with the most common type: ball bearings. Ball bearings use spherical rolling elements. Because the contact between the ball and the raceway is point contact, friction is very low. This makes ball bearings ideal for high-speed applications such as electric motors, fans, turbines, and precision instruments. They operate smoothly and efficiently. However, point contact also means limited load capacity. Under heavy loads, stress concentration becomes critical. Ball bearings are not designed for extreme radial loads or severe shock conditions. When higher load capacity is required, engineers use roller bearings. Roller bearings use cylindrical rolling elements. Instead of point contact, they create line contact between the roller and the raceway. This distributes load over a larger area, allowing significantly greater radial load capacity. Roller bearings are commonly used in gearboxes, heavy machinery, construction equipment, and industrial drives. But this increased load capacity comes at a trade-off: more friction and lower maximum speed compared to ball bearings. Roller bearings are also more sensitive to misalignment. Then we have needle bearings, a subtype of roller bearings. These use very thin, elongated rollers. Their main advantage is compactness. Needle bearings allow high load capacity within a small radial space. They are widely used in automotive transmissions and space-limited mechanical systems. However, needle bearings demand excellent shaft surface quality and precise lubrication. They are less forgiving under poor conditions. Finally, there are plain bearings, also known as sleeve or journal bearings. Unlike rolling bearings, plain bearings rely on a lubricating film separating the shaft from the bearing surface. When operating correctly under hydrodynamic lubrication, there is no metal-to-metal contact. Friction can be extremely low, and load capacity can be very high. Plain bearings are especially suitable for very high loads, low to moderate speeds, heavy shock conditions, large rotating shafts. In fact, large turbines, ship engines, and power plant generators often use plain bearings instead of rolling bearings. Each bearing type represents a different balance between speed, load capacity, precision, and durability. Selecting the wrong type is one of the most common engineering mistakes. A bearing designed for speed will fail under shock loading. A heavy-duty bearing may generate too much heat at high RPM. A precision bearing may not survive contamination. There is no strongest bearing. There is only the correct bearing for a specific operating environment. Contrary to popular belief, bearings rarely fail because they are too weak. They fail because the conditions around them are wrong. A properly selected and correctly installed bearing can operate for millions, sometimes billions, of revolutions. But a small deviation in lubrication, alignment, cleanliness, or temperature can dramatically shorten its life. The number one cause of bearing failure is improper lubrication. Rolling elements and raceways must be separated by a thin, continuous lubricant film. If metal surfaces come into direct contact even microscopically, adhesive wear begins. Heat increases. Surface damage accumulates. The process accelerates rapidly. Lubrication does far more than reduce friction. removes heat from contact zones, protects against corrosion, carries away microscopic debris, prevents direct surface welding. When lubricant degrades, becomes contaminated, or is insufficient in quantity, bearing life drops exponentially. The second major enemy is contamination. Dust, sand, metal particles, and moisture can enter even well-designed systems. A single hard particle trapped between a rolling element and raceway can create a microscopic dent. That dent becomes a stress concentrator. With every rotation, stress focuses there. Over time, a subsurface fatigue crack forms. Eventually, material begins to flake off, a process known as spalling. Once spalling begins, failure accelerates rapidly. Another critical factor is installation error. Improper mounting can introduce internal preload, misalignment, or uneven load distribution. Pressing a bearing incorrectly onto a shaft can damage raceways before the machine even starts operating. Misalignment causes edge loading, drastically reducing fatigue life. Temperature also plays a major role. Excessive heat alters lubricant viscosity, reduces film thickness, and changes internal clearance due to thermal expansion. What begins as a minor overheating issue can quickly become catastrophic. And perhaps the most important lesson, bearings are rarely the root cause of failure. They are indicators. When a bearing fails, it usually signals a deeper problem in lubrication systems, alignment, contamination control, load calculation, or thermal management. A bearing is a precision stress management device. It survives by controlling contact mechanics under repeated cyclic loading. When conditions are correct, it operates silently and efficiently. When conditions degrade, it becomes the first component to reveal the weakness. So in the end, a bearing is not just a rotating element. It is a critical interface between motion and control, between force and precision. And without bearings, the modern mechanical world simply would not turn.